Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome Stefan WAGNER, who is now in Sweden, right? And it will be a very dear to my heart topic of non-commutative principal bundles. So factor systems for non-commutative principal bundles and their applications. Floor is yours, the Zoom is yours. Take it away.
Thank you so much for the nice introduction and for the opportunity to give a talk here in the seminar. I will do my best to make you happy. I know that you like non-commutative principal bundles.
Okay. So Paolo likes principal bundles, right, Paolo?
Yeah, many people hopefully like them. So, okay. So this is what I would like to talk about today. So I will start with some preliminaries, talk about C-dynamical systems. Then I will tell you a little bit about non-commutative principal bundles, and then about their factor systems, and then what you can do with factor systems. All right, so let's start with the preliminaries. So I start with some conventions. So whenever you see the letters A and B, that will be unit or C-star algebras. For convenience, I will only look at compact spaces and compact groups. So P will always be a compact space.
And when you say compact, you really mean compact house, right?
Yeah, sure. Compact Hausdorff. Yes, this is what I mean. Again, G will be a compact group. I will tell you in a little while why I'm only focusing on compact groups. So some of the results also work more generally for compact quantum groups. All representations I consider are finite dimensional and unitary, and I usually write them as a pair, the representation and the representation space. And I write this guy here of G for the set of equivalence classes of irreducible representations. All right. So what do I mean by a C-star dynamical system? I simply mean a triple consisting of this unit of C-star algebra, the compact group, and the strongly continuous group homomorphism from G into the automorphism group of A. And whenever I have such a C-star dynamical system, I typically write B for the corresponding fixed point algebra. So these all elements in the unit of C-star algebra are A that are fixed by the action. And now, one of the reasons I'm only looking at compact groups is that in this case, I have the Peter-Weyl decomposition, which means that like every continuous, possibly infinite dimensional representation, A can be decomposed into its isotypic components. And I mean, you have these isotypic components, and I mean, you have these projections here. And yeah, so these are the spaces I usually look at. And why is that interesting? Well, the direct sum is a dense star subalgebra of A. So in this compact group setting, you can reduce problems to these isotypic components, or you can use this isotypic component as building blocks. So this is something I'm going to use heavily. All right, now for some examples, if you look at the one torus, and you can look at the map given by left or right translation in the argument, and this gives you a C-star dynamical system. And well, this is an ergodic action, which means that fixed point algebra is trivial. And since the group is the torus, we know that the irreducible representations are parametrized by the integers, and then you can, it's easy to see how the isotypic components look like. Well, they're simply multiples of these Fourier modes given by, so fk for an integer k maps c to theta to the power k. All right. And then how does this dense star subalgebra look like? In this case, it's just the Laurent polynomials. And then, basically what that means is that each function can be approximated by its Fourier modes. So this is what people know maybe from their analysis course. So this is classical Fourier decomposition. Well, you can generalize this to more classical actions. Well, whenever you have a right action of this group G on P, which is continuous, then again, this induced map given by the right translation in the argument, this gives you a C-star dynamical system. So this will be interesting for later purposes. All right. So these are commutative examples. So let's look at some non-commutative ones. Of course, the classical toy example is the quantum two tori. So you take some parameter theta, and then the quantum two torus is the universal C-star algebra generated by this unitary C and V, satisfying this commutation relation condition here. And then you can define an action of the classical two torus on the quantum two torus. Well, how do you do this? Well, I mean, for a couple of complex number, for a couple of elements in the two torus, an element in the two torus, it acts on U just simply by multiplying with the first component, and then the action on the generator V is by multiplying with the second component. And then this also gives you a C-dynamical system. And just as before, well, its fixed point algebra is trivial. That means the action is ergodic. And since now our group is the two torus, well, the irreducible representations are parameterized by C2. And then how do the isotypic components look like? Well, they're just multiples of these products here of U to the power K and V to the power L. All right. More examples. Here you also have the Heisenberg group C-star algebra. What is this? Well, it's the group C-star algebra of the discrete three-dimensional Heisenberg group. And this is the universal C-star algebra generated by three unitaries, U, V, and W. And then you have these relations. So U, W is equal to WU, VW is equal to WV, and then you have this UV is equal to WVU. So in particular, this means that W is in the center. And well, on this guy, you also have an action by the classical two torus. Well, how is this? Again, I mean, an element of the circle of the two torus acts on U by multiplying with the first component here. It acts on V by multiplying with the second component. And well, W is simply fixed by the action. And what you see, it is a C-dynamical system. And of course, what the question is, what is the fixed point algebra? And then you can see this is the C-star algebra generated by the element W, which is simply the functions on the torus. But it's a commutative C-star algebra. Why is this interesting? Well, this is related to C-star algebraic bundles. So you can show that this C-star algebra is a C-star algebra bundle over the torus whose fiber at theta, which is equal to x2 pi theta, is given by the two torus with respective theta.
Sorry, Stefan, just a small notational remark. Sometimes you write T2, sometimes you write T for your torus.
Yeah, but
that's just a slight inconsistency. When you write T, do you mean again two torus or something?
No, when I write T, I just mean the circle.
Aha.
And if I really write T2, I mean the...
Okay, sorry.
So
yeah,
T if you want, yeah. So
yeah, okay.
So it's a two torus then.
Mm-hmm.
Yes. Okay, this is what I mean. And I mean this C-star algebra, I mean, of course, there are many applications. One of the applications that plays a crucial role in the classification of non-commutative principal torus bundle in the sense of secret Echtdorf and Richard Nest. So this is one of the reasons I stumbled upon this C-star algebra. Maybe last but not least, the quantum SU2, of course, you take this Q between -1 and 1, and then you look at SUQ2, which is the universal C-star algebra generated by A and C, subject to this relations here. And then, well, you also have an action now by the one torus, so the circle. This is the so-called gauge actions on the generators, where you're just acting on the generators by multiplying with the respective element. And well, this leads to a C-star system, and it's the so-called quantum Hopf vibration. And its fixed point algebra is the quantum two-sphere. All right. So just now we've seen a bunch of C-star dynamical systems. So what I would like to tell you now is about the modules or associated modules and their monoidal structure. So whenever you have a C-star dynamical system and you take a representation of your structure group, then the following assertions hold. Well, we look at this space, so this is a associated vector bundle if you want. So what do I do here is I look at the tensor product of A and the representation space of sigma. And then on this space, I have a natural tensor product action. So this space is simply the fixed point algebra with respect to the tensor product action here. All right. Another C-star algebra, another space that is interesting is this C of sigma, which is a unital C-star algebra. So again, what I'm doing here is, well, I look at the tensor product of A and the operators on the representation space. And on this guy, I also I have a tensor product action by star isomorphisms here. And then the C sigma is the fixed point algebra of this tensor product action on the tensor product of A with the operators on V sigma. So what I would like to say is that this associated space, this gamma R sigma, is almost a Morita equivalence bimodule between this C-star algebra C sigma and B, so the fixed point algebra. So what are the left and right actions? Well, you can see easily that C sigma here, right, that acts from left side on the associated space, on this associated vector bundle. And then B acts in the first leg from the right side. So this acts here, and this guy acts from the left side. All right. So now for Morita equivalence bimodule, you also need an inner product. Well, I mean, on simple tensors, you just do this. You take A tensor V and B tensor W, and then you map them to the inner product of V and W. So this is one of the reasons why I consider unitary representation. So I have this inner product here on the representation space, and then I multiply with A star B. So of course this...
Stefan, sorry, could you tell us what is this C sigma algebra in the commutative setting? Because it's clear what is B, it's clear what is gamma. Yeah, these are the modules.
That's a good question. I don't think. I mean, I don't think it pops up naturally in the commutative setting. I don't know if we have any experts on this, but I mean, this is nothing you see in the commutative setting. I mean, even in the commutative setting, this is a non-commutative C-star algebra, right?
Yes.
Because of the operator space.
Yeah, but isn't it like the algebra of endomorphisms of vector bundle?
Aha, wait.
Yes.
Yeah, it could be. Yeah, sure. Yes. This is the algebra of, yeah. Because then this is simply aha, yeah. You have an operator in each fiber that acts fiber-wise. Yes, you're right. All right, thank you.
Because I remember this is what Mark was teaching me, so.
Yeah, sure. Yes. So this guy acts from, this acts then, of course, from the left. So
these are based endomorphisms of the bundle, right? I mean, they don't move. Okay.
They don't exactly. So they just act in the fiber. Yeah. So they're just vertical actions if you want. It leaves the base space invariant. Yeah. So again, this guy here has values in A, but since you start with this, I mean, since you can use this invariant property to show that this actually restricts to elements in B if you plug in elements in this associated vector bundle. And for the other side, of course, so what you do, you take simple tensors, you take A tensor V and B tensor W, and you map it to A, B star, and then to this rank 1 operator here. And again, by this invariance condition, it will end up in this C sigma. So now I have to explain what almost means. Almost means here that the linear span does not need to be dense. So whenever you start with a C-star dynamical system, anyone, it's not clear that this is a dense subspace. Or since it's unital, it must be actually everything. But I mean, in general, this is not clear. So this is the missing condition.
I'm confused by your second line, the restriction of blah, blah, blah to B. What do you mean? What do you restrict to B?
I mean, what I mean, so these are elements now in the tensor product, right?
Yes.
Tensors. Now, if I plug in elements in this gamma A of sigma, this will still be in A, but because of the invariance conditions, this will be in B. Yeah.
Sure.
I mean, I restrict. I mean the image to B then. Huh?
Yeah, of course.
So again, this is important for the rest of the talk, is that this is almost a Morita equivalence bimodule, and the only missing condition is that the inner product, the left inner product, is not dense. This is important for later on.
So I understand what you mean, but I don't understand why you wrote it like this, because if you restrict it, okay, so this is, okay, so I'm supposed, okay, so it's a restriction to this gamma lens in B, okay.
Exactly. And again, I mean, Morita equivalence means that the inner products are full, but you cannot guarantee that in them, so it's not clear. All right. So let me just say one relation to the isotypic components is the following. So whenever you start with an irreducible representation, then if you look at the tensor product of this gamma R sigma bar, where bar is the conjugate representation, and you tensor it with V sigma, then this will give you the isotypic component. So basically, these are the multiplicity spaces of the isotypic components of the action, if you want, like this. All right. Okay, a little bit more about these guys. So we have natural B bilinear isometric maps. So now you take this associated vector bundles, right? Then you take the tensor product over B, and then you can land in the associated vector bundles of the tensor product representation. I mean, how do you do this? Well, I mean, you take A tensor V, B tensor W, and then you just multiply take the multiplication the first leg here. And then you will end up in the right space. And now you have this for all representations, sigma and P of G, and then you can match them together, and then it satisfies this associativity condition. All right. And then what you can show is that the functor, which goes from the representation category of G into the correspondences over B, so each of these associated vector bundles is a correspondence, together with these maps, with multiplication maps for all representation, constitutes a so-called weak unitary tensor functor. Again, what I like to point out that if you start with the arbitrary C-star dynamical system, these maps are always isometries. So they are always injective. What we will need later is also surjectivity or dense range or whatever you want.
Okay, let me stop you here for a moment.
Yes.
Standard terminology when you deal with monoidal categories, you have a functor which is strictly monoidal, strongly monoidal, and monoidal. So I understand that tensor functor simply means that it's a monoidal functor, right?
Mm-hmm.
So,
yes.
So what does it mean in the common language, a weak unitary?
I mean, weak unitary
refer to the strongness or strictness Probably, surely it's not strict. And I guess without freeness, it's also not so strong.
Yeah, exactly. I mean, the weak refers to the maps are basically only isometries.
Okay.
Yeah. So I mean, exactly. In the free case, this will be unitary, as in the sense that this is isometric and surjective map.
Okay, so basically what you have is a monoidal functor, and then this weak unitary refers to this additional structure which is given to you by function analysis.
Exactly.
Okay.
And why I'm saying this, maybe this is just an interesting information for you. But you can actually show that there's a one-to-one correspondence between C-dynamical systems and this weak unitary tensor functors. So each C-dynamical system gives you a weak unitary tensor functor, and the other way around, whenever you have this weak unitary tensor functor, you can reconstruct the C-dynamical system. So this is a theorem by Sergei Neshveshev.
It would be interesting to know a bit more what structure this correspondence preserves, because I mean, having a bijection between two infinite sets is not such a big deal. The point is that there is some natural way to relate one into another, and this keys.
I mean, the interesting thing is really how the reconstruction from the tensor functor to the system. Yeah. So this is also what I use occasionally.
Mm-hmm.
All right. So these were the preliminaries. This is also, this is what I wanted to say about C-dynamical systems. And this brings me to my second point, to the non-commutative principal bundles. All right. So let me start with the topological definition of a principal bundle. So what is this? You have this quintuple consisting of a compact Hausdorff space now, P, space X, which will automatically be compact. It's compact group, and then you have these two maps R and Q, where R is this continuous action, which is free, and Q is simply a continuous and open surjective map. And especially this implies.
I'm sorry. Point number two, I'm confused. Q is a continuous open surjection, a special X is compact. I just don't understand the English.
I mean, you have a continuous and open surjection, and since my space P was assumed to be compact, also the image will be compact.
So what you mean is, in particular, when X is compact, then we have a following condition, right?
Yeah, I mean, I started with these conventions, and here in this slide I didn't say anything about X, but by my conventions, X will be automatically a compact Hausdorff space, but the X will not play such a big role, so I was just putting that in the second part of the point. Yeah, also by my definition, X will be a compact space. Since Q is a continuous and open surjection.
Okay. So
this is how I
talk. This is confusing.
Yeah, in this way, I put in the X. And then I have this, this satisfying these two conditions. And first condition is basically that the group acts on the fibers transitively and freely also. So the second point is that all fibers are G equivariantly homomorphic to G. All right. So I know that you really like this translation map. I mean, just here, I'm just saying that sometimes I just say, suppress the maps and just say P is a principal G bundle over X. Here, the translation map. So whenever I have a principal bundle in my setting, then I can show that this associated translation map, right, which goes from the fiber product over X into the group, well, defined by this property, is well defined and continuous. And usually these translation maps are part of the definition of a principal bundle, but in this compact setting, it's automatic, continuous.
Yeah, I mean, compactness guarantees continuity, yeah.
Exactly, yeah, because in this case, You have continuous bijection, and then the inverse image of this classical embedding map will be this translation map. All right. So let me also say something about this local triviality, where classically you're interested in principal bundles, which are locally trivial, which means that each point has an open neighborhood for which there exists a homomorphism from the Cartesian product to the inverse image over the open subset, satisfying this equivariance property. So locally, you want the principal bundle to look like a trivial bundle, and you want the identification maps to be equivariant. And let me just say that in the smooth category, so when everything you consider are Lie groups and manifolds, then each principal bundle is automatically locally trivial by the quotient theorem. So in the smooth setting, everything is locally trivial. All right, so I'm moving towards a non-commutative setting. So here I want to identify principal bundles with free actions. So that means if you start with a principal bundle,
sorry, I'm getting confused. Identifying principal bundles with free actions, it seems to indicate that there are principal bundles without free actions.
Yeah, I mean, let me try to explain.
Principal bundles with free actions. Sorry, I'm so sorry. Sorry.
Yeah. No, exactly. So what I mean by this, if you start with this more general definition, then you see that this projection map, it factors through the canonical projection. In particular, the base space is homeomorphic to the quotient, which means that principal bundles can be conveniently identified just with the free action. In this compact setting, having this 5 objects is the same as just the R, if you want, or the P and the G. So my takeaway here is that in the compact setting, principal bundles are the same thing as free actions. So the compact setting, so if you want to generalize this now to the non-commutative setting, what we have to do, well, I mean, this is a small exercise, of course. The following are equivalent, right? I mean, R from P times G to P is free. So this is maybe A, and then B is simply, okay, I mean, you have this map, I don't know, maybe you call it P times G into P times P, which maps P times, so the pair to P, and then the translation is injective. Right? I mean, this is a nice exercise for topology students. And then, you know, by non-commutative geometry methods, you just turn around the arrows, and then you end up with this definition. So my definition is a C-star dynamical system is called free if this L-Wood map, which goes from the algebraic tensor product of the C-star algebras into the functions on G with values in A, mapping a simple tensor, I mean, evaluating this on G gives X times alpha G of Y. So if this map has dense range, the C-star dynamical system is called free. All right. And of course, as you already mentioned, there are characterizations of freeness. You have the strongly monoidal functors. You have the Peter-Weil-Galois condition. And something that I will use later on is the following. For each irreducible representation, I have the unit in the left inner product that we saw before. Now remember, we had this spaces gamma R of sigma. They were equipped with the left inner product values in C sigma. And now I want that you can generate a unit, which means basically that this space, these associated vector spaces, are Morita equivalence bimodules. So this is the missing condition that I was pointing out from before. So freeness means that these associated spaces Amorita equivalence bimodules between C sigma and B.
Mhm.
So I capture, basically freeness is captured in these associated modules. All right. So let me say for just to justify it, this is a good definition. For continuous action, the following statements are equivalent. The action is free, and the induced C-state system that we've seen before is free in the sense of Elwood. And then, of course, this justifies to regard free C-state systems as non-commutative principal bundles. No? If you consider free actions as principal bundles. Now, of course, whenever you have fancy definitions, you would like to see a couple of examples. You see that your theory is not empty. So there are plenty of examples. For example, you have the quantum N torus together with its natural action by the N torus. And these are ergodic actions. Cross products. So whenever you have a cross product with a discrete abelian group D, then you have a natural action by its dual group. And then this is also a free C-state numerical system with fixed point algebra. So you recover the original algebra here. We saw the discrete three-dimensional Heisenberg group, or the group C-state algebra of this guy. This is also a non-commutative principal T2 bundle, and its fixed point algebra, as we have seen, is the circle or the functions on the circle.
And here in point number 2, when you mentioned cross product, there's no cocycle. It just
there's no cocycle. Exactly, there's no cocycle. But in fact, it doesn't matter. Actually, when you work with cocycles, it's still free.
Yes, but of course, yes, you're absolutely right. But I think it's a very good point to observe that in case there is no cocycle, these are precisely trivial or trivializable non-commutative principal bundles.
Exactly. Yeah, I will talk a lot about cocycles. So I thought at the moment I will omit them. So all right. So then, of course, the quantum Hopf vibration with its natural gauge action is an example of a free action or free C-state system. So a lot of people right now work with graph C-state algebras or algebraic versions of this. So whenever you have a graph with finitely many vertices, then the gauge action on the graph C-state algebra is free if and only if the graph is row finite and has no things. And finally, so now you've seen examples where basically only compact abelian groups are acting, but you also have this Conlandi spheres, which is a non-commutative 7 sphere. And this comes equipped with an action of SU2. And then you can show that this is a free action with fixed point algebra, some non-commutative 4 sphere. So what I'm saying is there are plenty of examples. All right. A couple of reasons why you should be interested in these guys is, of course, the study and classification of actions of quantum groups on C-state algebras is interesting. Then you have relations of this free C-state algebra system to Fell bundles, Hopf-Galois extensions, and strongly graded rings. So you can, jump around between these different kind of point of views if you want. And then you have plenty of applications to analysis geometry and physics. For example, non-commutative Riemann geometry. But these non-commutative principal bundles are also interesting for KK theory, of course, for non-commutative gauge theory and quantum field theories and T-duality, which is a symmetry in string theory. All right, very good. So I hope I made some a good impact on free C-state numerical systems or some non-commutative principal bundles. So now we are already at point 3, because now I will tell you about the factor systems that you can associate to this free C-state numerical systems. And before I do this, I thought I start with some classical factor systems where you might have encountered them. So usually they pop up for non-abelian extensions of groups. So it was Schreier in 1926 and Eilenberg-McLean in the 1940s. They developed a classification theory of non-abelian extensions of groups, which led to low-dimensional non-abelian group cohomology. So what is the idea here is the following. So whenever you have a non-abelian extensions of groups, so this guy here, you take a normalized section of the surjection from E to G, and then you can associate some data. And what you're doing here is, so for each element in your group G, you associate a group automorphism of N simply by saying, okay, what happens to N? Well, I just conjugate with the image of S with respect to G. So this gives me an automorphism of N. But then even for every pair here of elements in G, I can associate an element in N that I call W. And how do I define this? Well, I define this as S of G, S G prime, and then I take the product G G prime, apply S, and then I look at the inverse element. And then since it's a section, this guy will end up in N. So because if you project it down, this will lie in a kernel, which means that the element you started with must be an element in N. All right. And then whenever you have this, or this family consisting of these automorphisms and these elements is called a factor system of this non-abelian extension of groups. And then sometimes, for ease of notation, you just write S and W. Okay.
That's exactly what will give you a cocycle, this omega, right?
Yeah, the omegas are the cocycles. Yeah, absolutely. I mean, depending on the theory, if you have central extensions and or abelian extensions, everything is a bit nicer. Here you have, of course, I mean, in non-abelian case, these cocycles are a bit more involved.
Mm-hmm.
So why would you do this? I mean, do you see this factor system that consists of data that only depends on N and G? So what it means, you can actually forget about the section and well, just look at the conditions these guys satisfy, and then you have these two conditions. This is the cocycle condition. And this is what is called an outer action. So basically you have these two conditions here. And what's the fun part is...
Sorry, Stefan. Can you explain why the factor system does not depend on S? Why?
No, I mean, what I'm saying here is...
Omega is defined in terms of S.
Yeah, no, absolutely. But what I'm saying here is that, I mean, you get information that only depends on N and G, right? I mean, what I'm saying is you can formulate this abstractly, right? So you can say what a factor system is without
the conditions. Okay, right. Okay.
So, and this is the whole point, because all the information is encoded in the factor system, which does not depend anymore on E or the section S. So once you have a factor system, you can actually recover E or the extension. So this is the whole idea. So you have a group extensions, and with this factor system, you can recover all informations about the big in terms of N and G.
Yeah.
All right. This is the idea. So at the time, when I was a PhD student, my supervisor, he worked a lot on this non-abelian, but in finite dimensional Lie groups and their factor systems. And so I was a little bit interested in principal bundles. So at some point, I was just wondering, well, is it actually possible to have a similar theory for principal bundles, or let's say non-commutative principal bundles? So here's the idea. So you have this free C-static in a system, and you would like to consider the big algebra A, so if you want the total space, as an extension of B by G, whatever that means. And the problem is, I would like to associate data with B and G that contains all the information about the C-dynamical system. So again, just like with group extension, I would like to have data associate B and G that recovers the C-dynamical system. All right.
So what do you mean by this arrow from A to G?
That's just that's just abstract nonsense. This is just like to have an idea. I mean, just you know, you have similarity to the case of group extensions. So here, this is just like quotation marks, just as an idea that somehow A should be an extension of B by G. So far, it's just an idea, and we would like to make this idea precise in a moment. All right. So why would you like to do this? Well, this makes free C-statistical systems accessible to classification. So that was one of the reasons I did this. Was I was wondering if you have this free C-statistical systems, and for example, if you look at the definition of the Elwood condition, this does not involve the fixed point algebra. So my question always, how can you classify them? So you need a good characterization of freeness to find a classification, and this factor system actually help to classify this free C-statistical system.
So classify fixing B and G.
Exactly. Yeah, you start with B and G, and then you ask how many, what kind of free C-statistical systems exist with structure group G and fixed point algebra B. Because we come back to this later. And then, of course, then you would like to study permanence properties. So you have properties on B and G, and you would like to pass them over to A. So this is also something that I would like to discuss later. Basically, the idea is, you know, if you have a spectral triple on B, so some kind of smooth structure, and you have a Lie group on G, you want to use this information to endow A with the spectral triple.
Sorry, here, Ludwig and Andrzej, didn't you write a paper in this respect about inducing spectral triples from the base by the circle action?
Well, this was just case of the circle, and then we tried torus and some particular cases with spectral triples. This is more general, I think.
Yeah, but you did something in that direction.
Yeah, I think it was the first something missing principal boundaries and spectral triples. Algebraic principal boundary spectral triples.
Yeah, and then I also, of course, at this occasion, I have to thank you guys, because of course, it was you who inspired me and my co-workers to generalize this to the class to the more general case of G compact case, not only compact abelian. Exactly. So these were the guys who did it first, and then I was so lucky to use this or put this in a more systematic way for general actions. Then K-theoretic considerations. So I come back to this later. And of course, you would like to have invariants and characteristic classes for the C-dynamical systems. And also, maybe if I have time, this also helps to do computations in general. So usually, if you just have any kind of structure, sometimes it's hard to do computations, but with this vector system, you can actually do some computations that tell you something about the structure. All right. So here's a characterization of freeness. So you have a C-dynamical system, and then the following statements are equivalent. A, your C-dynamical system is free, and B, for each irreducible representation, there's a finite dimensional Hilbert space and an isometry in this tensor product from A into L, operators from the representation space into this finite dimensional Hilbert space, satisfying this equivariance property. So basically, if you apply the action from the left side, then it's the same as multiplying with the representation from the right side. And this is a very compact notation. Of course, there are tensor products involved, but they're implicitly notations that are compact.
Isn't it like an incarnation of strong monoidality?
I mean, it's related, of course, because these are all equivalent characterizations. But the point really is here that you find this isometry.
Yeah.
I mean, before you had this isometric maps, but it's not necessarily the same thing.
There's a finite Hilbert space H sigma and an isometry.
So of
Okay,
course,
yeah.
of course, I will help you a bit here. How does that look? I mean, how does it look like in the quantum two-torus case? Here, again, the irreducible representations are parametrized by C2, and here you may choose these Hilbert spaces to be one-dimensional, and then you just, well, so what is your isometry? It's just the product of the generator, so u to the power k and v to the power l. And I mean, you see that this equivariance property is easily satisfied because if you apply the character, I mean, if you apply the action, this is just multiplication by the corresponding character.
And how about the quantum Hopf vibration? What are the isometries then?
Perfect. You're ahead of your time. I will discuss this in a second. Let me just say, because we talked about cleftness, so you see in the quantum two torus already here, it's not only an isometry, but it's a unitary element.
Yes.
But if these isometries are unitaries, then I call this cleft, and this is an interesting subclass. Interesting in the sense whenever it's cleft, you can show that that A is actually cross product. So cross product in the sense of an action and the cocycle of B and G. So cleft.
So let me comment here. I love it because it's something which we're craving for. You see, cleftness is something very natural in Hopf theory, but somehow, you know, you use this convolution, invertibility, and we were thinking that it's maybe too difficult to do it in the context of sister algebras. I remember I had a conversation with Nigel Hickson about it. Okay, so we know very well about how to handle really cross products without cocycles, but we have this concept of cleft Hopf extension. How do I do cleft at the level of sister algebras? And I remember Nigel tried to convince me there's no hope of this because the antipode are unbounded, nothing will work. But I love this condition. It seems so natural, and if it's tantamount to the usual cleftness, then it's great.
Yeah, I mean for G equal to the torus, this is exactly cleftness in the Hopf-Galois setting. Yeah, otherwise it's generalized.
But I understand you have no problem doing it for quantum groups, right?
No, you do the same thing. I mean,
Yeah.
this is exactly one of the one of the cases where you can look at quantum groups as well.
Yeah.
I mean, this whole freeness also works for quantum groups.
Well, that's obvious, but cleftness was not obvious.
Oh. All right. So, I mean, basically, and what cleftness means is that you can factorize A into the fixed point algebra in the group. All right. But you asked already for the quantum.
Yes.
Here you get it. You already know this is free. And now, of course, the question is, how do the isometries look like? And here, I mean, the good thing is that, I mean, the irreducible representations are just the integers. So basically, it's enough to look at only one element here. So the element that I'm referring to that characterizes the freeness here is simply this, this.
Sorry, but I must object to this notation. A quantum group is not its algebra. You should really write the algebra of SUQ2, not SUQ2 itself.
Okay.
Yeah, you know, we have the concept of quantum spaces, and that's the dual category.
Yeah.
And it really makes sense. So that's, you know, typically physicists use such lousy notations, but that's really bad. But okay, something more interesting, if I may, is that AC, it looks to me, this is exactly what you're talking about, is the associated Hopf line bundle. That's exactly the section module.
Yeah, and exactly. So this is exactly good that you say this, because, you know, this is also something you will see in a second, how this is related to the associated vector bundles. Yeah. Because I already told you before, right? When you have a C-star dynamical system, you have the associated vector bundles. And this is exactly the projector corresponding to the line bundle.
Yes.
Exactly. Yes. Absolutely. So very good. I mean, and then once you have this, then you can generate the other ones just by, I mean, you look at this n-fold tensor product, and these are the elements here, where the sub-indices refer to the lag numbering in the respective tensor product. So I mean, whenever you have a torus bundle, it's usually enough to find only one of these elements, and then you can generate the other ones.
Can I ask you, Stefan, so you in general you can find also other Hilbert spaces which work, or this is kind of unique, this H Hilbert space?
Yeah, you can definitely, exactly, you can find other ones as well. Absolutely. This is not unique. You just need one and then it works. And I will tell you a little bit about, I mean, about equivalence, because you can find other ones, but then the question is, when do they generate the same C-dynamical system and these kind of questions?
Okay.
Absolutely. This is just one one element that satisfies this requirement, but you can find other ones. Absolutely.
Okay,
but I mean, this is not right. I mean, the characterization here is just there is one. Doesn't need to be unique. All right. And then, I mean, for negative integers, you just look at the partial adjoint. Maybe interesting something. I mean, now we go back to the classical case, because let's say you have a closed subgroup of G, and then of course the canonical right action gives you a principal bundle over the quotient, right? And now you would like to establish freeness algebraically, so in terms of these isometries. And here you apply the Frobenius reciprocity theorem. So for each irreducible representation of H, you find this finite dimensional representation of G here. So here comes your H sigma, and you find this isometry from V sigma into H sigma such that you have this commutation relation. And then you can define this isometry by putting, okay, so I mean, this will be the function in G with values in the space of operators. So what you do, you evaluate on G, and this is simply the composition of the isometry and then the representation evaluated in G. So this will be the thing that characterizes this principal bundle algebraically in terms of these isometries.
Can you recall what is int? IND?
Yeah. Can
you recall what is this IND? Perhaps you said this before.
I mean, I use this Frobenius theorem. Also, so whenever you have
Okay,
this,
so there is a representation. Okay, I understand.
yeah,
Which is
exactly.
two lines
So this is
okay.
this is related to induction.
Okay.
So induction procedure, exactly. So there's this very nice paper by Mark Riefel about this direct operators on homogeneous basis. All right, so that was just to give you a little bit, to give you a feeling how these isometries look like. Let me also tell you something about, well, let's call it patchwork, because I mean, I said we have these isometries, but these isometries in the Hilbert spaces, but you can patch them together. So what do I mean here? You define this Hilbert space, right? For each irreducible representation, you look at the Hilbert space that has this, this is the irreducible representation, and this is the multiplicity space. And on this guy, you have a natural representation. Well, here, right on the second leg, you just act by the respective representation, and then just by one on the H sigma. And what the idea behind this is that this representation mu H is a generalization of the left regular representation. So we will use this also a bit later. What I'm saying here is basically, okay, this was just a Hilbert space H. You can do the same thing with the isometries, and then you get a big isometry on this Hilbert space here. Again, I mean, what you do, you take the sum over all the reducible representation, you tensor with one, and then you end up in this Hilbert, I mean, this space of operators, and then you see that this S is gonna is an isometry. What why I'm saying this, this gives you a more global characterization of freeness. So the following statements are equivalent. The C-dynamical system is free, and there exists a possibly infinite dimensional unitary representation, mu and h. So you saw on the last slide how you get this h and the mu, with finite dimensional multiplicity spaces. Let me just say that this finite multiplicity space is going to be super important later on if I have the time to talk about this spectral triples. So it's important that this representation has finite dimensional multiplicity spaces, and then given a covariant representation, you have these three conditions. So the first thing kind of says that S is a multiplier somehow, and then you have this equivariance conditions here. So this is something we're going to use later. I mean, of course, it's a bit heavier to read, but it's very useful for applications. All right. Let me come back.
Could you go back, please?
Yes.
I'm wondering, because you use this quantifier for every G in G. So can we really make it into quantum groups?
No, this here works. This we have only worked out for.
Okay.
Well, actually, so this we have only worked out for groups, compact groups. Yeah, because later on, I mean, in this application where we use this, try to build the spectral triples on A, we only work with classical groups, so with a compact Lie group. So it's not so clear how to generalize this to quantum groups here.
Okay, thanks.
Okay, let me go back to this characterization. And I thought like every presentation should include a proof. So I thought you might want to see how the proof works in this case here. So we would like to prove B to A. So let's say you have this family of Hilbert space and isometries, and you would like to prove that the C-dynamical system is free. And what I would like to use here is that the left inner product generates the unit, because this is one of the equivalent conditions for freeness. This is what I try to point out, that this is something that is important here. All right, and then well, you take any irreducible representation, and then you take an orthonormal basis or basis of the Hilbert space A sigma. Okay, and then, well, right, I mean, this guy is now here. I mean, if you take the star, I mean, only the spaces, they switch. And then you plug in the basis, EK, and yeah. So this is just the columns of S sigma star, right? I mean, you can consider this as an operator with values in A. And this S sigma star K, they're now the columns of this operator. And what you can show then by the equivariance property of this S sigmas is that each of these guys will lie in this associated vector bundle. And then you show that, okay, then you really do some, I mean, it's really just matrix computations. So so what I'm saying now, if you plug in these elements here, these columns, and you sum from 1 to n, you see that this is, you're gonna see that this is exactly the same as S sigma star S sigma, but since S sigma was an isometry, this will give you the 1. So the proof B from A is basically only, well, it's a matrix computation using the equivariance properties here, right? And I mean, the inner products here, so the problem is, I mean, you really want them to be in these spaces here. So this is why you do it this way. All right. For the other direction, so you start with the free C-dynamical system, and now you want to get these isometries. we need this lemma. And I mean, this is well known to most experts, I guess. So whenever you have a Morita equivalence bimodule between C-star algebra C and D, then you can find elements such that yeah, the sum over the inner products here is equal to 1. And by using this Morita equivalence compatibility condition, you can even show, I mean, this is kind of a yeah, Fourier decomposition. You can write each element X in this way here. So this is something we're going to reuse for the proof from A to B. So again, so we would like to, we assume freeness, and we would like to get these isometries. So you start with an irreducible representation, and due to the freeness, we know that the associated vector bundles are Morita equivalence bimodules, which means that you find elements in gamma A of sigma such that the sum of the respective inner products gives you the 1. Well, and then it's super easy. I mean, now you have n of these elements T, so you just put H sigma to be C to the power n, and you denote by T. This is going to be an element from A tensor, the operators from Cn to V sigma. It's the element with columns T1 to Tn. Again, this is just matrix computations. And well, then you see by definition that they satisfy this equivariance condition, and that T star is going to be equal to 1. And this is just a small computation. And then you just have to reverse the order. So you take S to be equal to T star, right? Because you want an isometry, so you have to reverse the order. Okay, so this is how you get your isometries. Very good.
Ludwig, may I ask Ludwig a question?
Yeah.
Yes.
When I'm looking at these calculations, it's a little bit like déjà vu, because they look to me like calculations we so often did with strong connections and the legs of strong connections. Is it just my feeling, Ludwig, or do you share my observation?
Must be related to strong
Yeah.
connections, yes.
Because it's exactly the same type of reasoning all the way.
All right. But I mean, if you say this, I would at some point maybe really like to discuss this with you, because at some point I thought about strong connections in the Hopf-Galois sense, but I didn't see connections. But if you see this, perfect, because then we can discuss this.
Yeah. I mean, because look, basically what happens. What is a strong connection? Strong connection goes from your Hopf algebra to the tensor product of your algebra of a total space, so to say. So in your case, fine, it's a commutative algebra of a classical group. That's fine. And basically, what we have is equivariance properties. I can see the equivariance property written there. And the thing is that if you multiply the legs of a strong connection one way, you must always get something like 1, which is what you have. And if you multiply the other way around, then you get a projection of the associated module. So that's, I cannot nail it down right now, compare notation and so on, but somehow the pattern, you know, sort of, that's something which would be hard for artificial intelligence to grasp, perhaps. But this is what humans can see. Verbatim, it's something completely different. Yeah, if I were a computer, I wouldn't notice it. But I have a feeling that we can very easily make a connection. But it's definitely not for now. Let's carry on.
I mean, at some point I started a project, I mean, working out these strong connections, but I got lost in topology problems and multipliers and this kind of stuff. But yeah, maybe it's something we can discuss.
Yeah, I'll be more than happy, yes.
All right. Anyways, so this was the proof. And so now I would like to tell you about the factor system. So we fix a free C-star dynamical system. And also, you know, for each irreducible representation, we choose a Hilbert space, H sigma, and such an isometry as before. All right.
Mm-hmm.
Then by taking direct sums with respect to irreducible subrepresentation, you can extend the H sigmas and the S sigmas to arbitrary representations of G. By arbitrary, I still mean finite dimensional representations. And then, just as before, remember, you know, these S's, these isometries, they somehow correspond now to the sections in the group extension case. And then you got an automorphism just by conjugating. And this is what you do here. You get a star homomorphism from B into this tensor product. How do you do this? Yeah, well, you conjugate by S sigma. Right. Also, in the group extension case, you got this element omega, which was an element in B, in the normal subgroup. So you get something similar here. So for each pair of representation, what you do is you multiply S sigma with S pi, and then you look at the S corresponding to a tensor product representation, and then you star it. And then this guy will end up actually in B and then something. So you see, I mean, starting with the C-star-dynamical system, you associated things that only depend on B and the group, or representations of the group. And then you do some computations, and then you have the following twisted co-cycle conditions. Well, these omegas are partial isometries, so this is the first line here. The second line is the so-called co-cycle or co-action condition. And the last one is the co-cycle condition. This co-cycle condition. So what I would like to say is, once you have these guys, they satisfy some conditions. All right. And then this triple consisting of Hilbert spaces, star homomorphisms, and these elements omega, this is called a factor system associated to the C-star-dynamical systems and the isometries you started with.
So H is a Hilbert space, omega is a cocycle. Can you remind me, please, again, what gamma is?
It's the conjugation by S sigma, which is a star homomorphism. Which is this guy.
Ah, because when you have something like a cleft extension, at least in the cleft extension, you have both action, which is by conjugation, and cocycle.
Yeah, and I mean exactly. I mean, in the case of a cleft action, this is just a conjugation by unitary element.
Yeah.
All right. So this is called a factor system.
Mm-hmm.
Let me also say, now some people might say, aha, it's very complicated. These are some crazy elements and some C-star algebras. Yeah, true. Anyways, if you have a compact abelian group and your C-star-dynamical system is cleft, then actually everything you just saw before is classical co-cycles on a dual group. So then you're safe here. All right. Just how do the factor systems look like for the quantum tori? And you have the generators, and then you take a pair of elements in C2. And we saw already before that you can choose the Hilbert spaces to be one-dimensional, and these are your isometries or unitaries. And in this case, maybe it's not surprising at all, because it's cleft. I mean, the coaction will be trivial, because the conjugation gives trivial maps. And the cocycle is exactly the one you expect here. So, all right. And then there's the reconstruction theorem, just like in the case of the group extensions, is that the multiplication, the involution, and the actions are completely determined by the factor system. So how does that look like? Well, it looks...
Sorry, Stefan, could you please explain to me what you mean by involution?
Aha, of course, the C-star algebra comes with an evolution, right? The
Yes.
star. Yeah, and I can recover the star in terms of the factor system.
Ah, so the star structure which are given on components induce uniquely a star structure on the...
Yeah.
Okay.
I mean, of course, for group extensions, this does not pop up because there's no evolution. But I mean, basically what I'm saying is I can recover the C-star dynamical system from this data. It means I also need an evolution.
Yes.
So how do the isotopic components look like? Well, I mean, I take an irreducible representation, and here you see, so I have the S sigmas, all right, and I just multiply from the left side with elements of this form. So basically, the isotopic components are completely determined by my isometries and then elements in B, and then this tensor factor of operators. So this is how my this is how the isotopic components look like. And for the quantum tori, well, this is not surprising. Well, then you don't have a trace, and then it's just multiples of u to the power k and v to the power l. How does the action look like on the isotopic components? Well, I mean, we know that these are the elements in the isotopic components, and now I have to tell you how do they act. Well, again, it must be something of this form. And what I do here is just multiply with the respective representation from the left side. All right. And then, I mean, again, for the quantum tori, this is kind of obvious. This is just multiplying by the respective character. Okay. The multiplication now is interesting. I mean, so people who work with the with group extension might see directly what's happening here. I mean, now I have two isotopic components, one corresponding to sigma and one to pi. And then I want to multiply elements in the isotopic components. And how do I do this? I mean, forget about the trace. So I multiply gamma sigma, and then I apply gamma sigma to y of pi. Then I multiply with the cocycle, and then I have the isometry that corresponds to the tensor product representation. So again, the multiplication between isotopic components is captured by the S, by the omegas, and by the gammas here. And then again, for the quantum tori, I mean, it's kind of obvious here, right? I mean, there are no gammas, and then this is exactly the omega that you expect here. The involution is a bit more tricky. Let me just say that how do you involute an element in the isotopic component? Well, you get something. The something has the star of the isometry here. And then you have this map gamma, j of y. And you have this formula here, how j looks like. So I mean, these are a couple of things that also come from this identification between unitary tensor functors and C-star dynamical systems. So this is a little more technical. In the quantum torus case, this j is just a conjugation here. All right. I wonder if I want to say something about this. Yeah, maybe I want to say something about this. So a corollary of all of this is basically, well, I told you before, you can patch together the isometries in the Hilbert spaces. And what you can show then, you can realize each free C-star dynamical system as the fixed point algebra of a coaction on the C-star algebra. So what I'm saying here is you have a coaction from D into the multiplier algebra of D times the group C-star algebra to C-star algebra. And then the free C-star dynamical system is the fixed point algebra of this coaction. I mean, this is a nice way to characterize C-star or to realize C-star dynamical systems. All right. Which brings me to applications now. I still have 50 minutes, I think.
Yeah, you have 15 minutes and 40 seconds.
Okay, then I hurry. Quickly, I mentioned classifications of non-commutative principal bundles. So again, so right, classically principal bundles. So you fix a structure group and you fix a total space, and then you would like to classify them. And classically, you can do this with check homology, but then you only consider locally trivial ones. All right. Anyways, you can ask the same question in the non-commutative setting. You start with the base. So what is the unital C-star algebra B and the structure group? And they would like to classify all free-star chemical systems with the structure group G, which have fixed point algebra B. And so just as in the case of group extensions, you define what an abstract factor system is. Again, you start with this unital C-star algebra, the compact group, and then a factor system for this pair here. This consists of finite dimensional Hilbert spaces, which you can extend factorial to all finite dimensional representations. And then you want a family of star homomorphisms for each representation. And then you want to have these maps, these elements omega for each pair of representations, satisfying this twisted co-cycle conditions from before. And a remark, of course, each factor system of a free C-star system is a factor system, is an abstract factor system, just like in the case of group extensions. And here we'd also like to, you need a notion of comparing factor systems and C-star systems. And then, of course, two free C-star systems are called, with fixed point algebra are called equivalent if there's a G equivalent isomorphism that is the identity on B.
Yeah.
And then maybe without going into detail, there's also a notion of conjugacy that tells you when two factor systems are equivalent or conjugated if you have these partial isometries. And it's maybe not so important. What I'm saying here is that the following theorem, so two free C-star systems, AG alpha and A prime G alpha prime, with fixed point algebra B are equivalent. So they're isomorphic if and only if their factor systems are conjugated. Moreover, each factor system, this is the interesting point maybe, whenever you start with this abstract factor system, this gives rise to a free C-star system with fixed point algebra B. And all this together tells you that there's a bijective correspondence between the set of equivalence classes of free C-star systems with fixed point algebra B and structure group G, and the set of conjugacy classes of factor systems for BG.
Yeah,
So,
I don't like the formulation. I think you have something much stronger because just bijective correspondence between two sets is not so interesting. And I believe that you have this equivariance goes into conjugation, and this way you establish having this bijective correspondence, it's much deeper. It's not just a stupid bijection. I think it's something very, maybe not canonical, it's natural in some sense. And this should be highlighted. I mean, the result, I believe you have is much stronger than what you claim.
I mean, actually, first of all, this also works for compact quantum groups.
Sure.
And then, as you say, of course, the more structure you have, if you have compact abelian groups acting, then you have really nice classification theorems in terms of group homology and all kind of things. But yeah, sure, maybe you can formulate this also in a different way.
And we wanted to say that the above defines bijective current. The above what you said before defines bijective.
Yes, exactly. This is already much stronger.
The above, what do you mean? Sorry?
We presented before.
Oh yeah.
Yeah.
Oh yeah, okay. Yeah. I mean, the third point is exactly. I mean, here you just, in the third point, you just want to say like, basically would like to know how many they are. I mean, exactly, this is not so much information, but maybe for some reason you would like to know if there exist any, or how many principal bundles exist. All right. So maybe the rest of the time I will talk about this lifting spectral triples. I have more applications, but maybe not so much time. But yeah, Well, okay. Let me quickly say something about spectral triples, but most of you, of course, know this. What I mean by a spectral triple is this quadruple, where A0 is a dense unital star subalgebra of A, H is a Hilbert space equipped with the faithful star representation, and D is a direct operator, so a possibly unbounded self-adjoint operator with compact resolvent and bounded commutators. All right. Well, this you know, this is the spectral characterization of spin manifolds, is that if you have a commutative spectral triple with some XOR structure, this is basically a spin manifold, right? So this justifies also to consider spectral triples as non-commutative spin manifolds. Then there are a couple of reasons why this is interesting. They provide a frame for quantum metric spaces, and well, from a non-commutative geometry point of view, it allows to extend many techniques from Riemannian spin geometry, like the dimension, smoothness, orientation, volume forms, and integration. And also they have applications. They have, provide a non-commutative formulation of the standard model and the quantum Hall current. And then they have applications in quantum field theory, and of course also in optimal quantum transport via the so-called Wasserstein distance. So what is my problem? My problem is the following. I have a compact Lie group, and I have a free C-determinant system with fixed point algebra B, and I have a spectral triple on the fixed point algebra. So again, I have some kind of maybe smooth structure on B, and I have a smooth structure on a compact Lie group. So the problem is construct a spectral triple A that is built upon the geometry of this of the base and the structure group. So I mean, here I have some geometric data, here I have some geometric data, here I only have topology, and I want to use the building blocks to give me some geometric data on the space A. And yeah, using this factor system theory as a key feature, we were able to provide systematic construction of such a spectral triple. And this has also relations to KK theory, because this operator, the Dirac operator that we constructed, is an example of the constructive Kasparov product.
Sorry, Stefan, before I forget, are you aware of some recent work of Mesland and Čačić? I think they're doing exactly such things.
Yeah, I'm absolutely aware of this. Yeah. So yeah, exactly. I mean, it was interesting that appeared somehow at the same time. Yeah. Yes. So the procedure is splits into the following 5 steps. First of all, right, you would like to construct a set of smooth elements, so some dense alpha equivariant and unital star subalgebra of A. And then what you need to do is to extend the faithful star representation on B to faithful covariant representation on the C-star dynamical system on some Hilbert space HA. Then you would like to construct, and I'll call that a DB connection, but basically what you would like a horizontal direct operator, or direct type operator that had bounded commutators with A0. And then you would also like to construct a vertical component of a direct operator via the group action. And once you have all this, you just need to assemble the horizontal part and the vertical part. All right. In the setup, so what you do is you choose a factor system associated with some isometries. So the whole construction depends on a set of isometries somehow. So it would be interesting to know how much it depends on the isometries. And you also assume that the factor system respects the B0 in the sense that, well, it maps B0 into B0, and also that the elements W, they lie actually in B0. So this is one of the assumptions we use. All right. How do you lift the smooth algebra? So we saw just before how the isotopic components look like in terms of this isometries, right? They were of this form, where Y was something in B. But now I just take, okay, well, I don't care about B, I want something smooth. So I just look at the elements that lie in B0. Well, and this gives me a dense alpha invariant in united star subalgebra, so that the invariants are exactly B0. So this is how I get my smooth star algebra. Again, this A0 depends on the isometries. It's characterized by the fact that it's the smallest star subalgebra satisfying the properties that B0 is in A0 and that S sigma is in the tensor product of A0 and the operators here, which in turn means that any other choice of isometries lying in this tensor product yield the same subalgebra. But again, this refers, I mean, this is one of my points, open questions, is how much the construction depends on S sigma. All right. So now I'm back at this unitary representation of G on this possibly a finite dimensional Hilbert space. So again, here I patch together the finite dimensional Hilbert spaces. And I also have this isometry, as I told you before, that this is some kind of multiplier. And what I can show is that the projection S star is a multiplier in this tensor product of B and the compact operators on H. And that A admits a faithful star homomorphism on this multiplier algebra. And then, well, putting P, well, I just apply the representation tensor identity. Then I get a projection in the operators on HB and H. And then I get a Hilbert space by projecting down the tensor product HB and H with respect to P. And then we get a faithful star representation in this way of A on the Hilbert space HP. And I have a unitary representation of G on HP. How do I do this? I just tensor U with 1B. Well, and then it's easy to see this is the unitary representation. So what I'm saying here is that the pair consisting of PA and UA, this is a faithful covariant representation, and it extends the representation PB in this sense here. Okay, so this is second step. Yeah. Let's see. Again, so for each irreducible representation, I can look at the projection here. By assumption, this lies in this tensor product where now I have a B0. And then I can look for each irreducible representation at this operator, this unbounded operator here, where I just cut down. So what I'm doing here is I look at the operator dB, I tensor it with the unit operator on H sigma, and then I cut it down with respect to the projection. This is an unbounded operator. It's self-adjoint and has compact resolvent. And then just by passing over to the Hilbert space direct sum, I can show that there's an operator which I call DH on the direct sum. And well, it extends dB in this sense, it's equivariant in this sense. And then under some relatively minor conditions, I can show that DH has bounded commutators with H0. All right. And I mean, for those people who work a little bit with KK theory, this DH, the horizontal part, is a dB connection. I just wonder, I'm running a little bit out of time here, but
50 seconds.
Sorry? Okay.
50 seconds.
No problem. I fast forward. Basically, what I'm doing here is, so I take the action mu, and the action mu gives me a vertical operator. with compact resolvent, and here that it has compact resolvent is basically due to the fact that it has finite dimensional multiplicity spaces. So this is where I really use the freeness as well, because there now I have this finite dimensional multiplicity spaces. In this way, I get a vertical Dirac operator. And so maybe one of my final slides is then, so I have this reference operator where I take just dB with the unitary operator, with the one identity operator of H, and then I have the identity operator on HB, and then I tensor it with dV. And what I do then is I take the projection to cut it down, and then I get a sum of these guys here. And the following assertions hold. This is a self-adjoint operator and has compact resolvent. It has, under some relatively mild condition, bounded operators. And maybe what is interesting, because I think the constructions that are known didn't have this property, is the horizontal and the vertical part, they anti-commute. Yes. So, yeah. So this is an application of these vector systems. Now, of course, my time was running out, so there's more things to do and more applications of vector systems, but maybe another time then.
Okay, so thank you so much. Okay, I believe that today the honor of asking the first question should go to Elmar Wagner. Elmar Wagner, do you have any question to Stefan Wagner?
Yeah.
Thanks for the invitation, but I'm fine. Thanks. It was good talk. So I will go on this time. I will think.
Okay, excellent. Now, please allow me to begin before I forget. There is a paper, recent paper by Mitchell Djurdjevic. By recent, I mean it's not even 30 years old. It's 1995. It's called Quantum Principal Bundles and Tanaka-Klein Duality Theory. I would strongly recommend that you look at it because it's basically, let me read you the abstract. The structure of a quantum principal bundle is studied from the viewpoint of Tanaka-Klein duality theory. It is shown that the structured quantum group is compact, which is what you assume. Principal G bundles of a quantum spaces are in natural correspondence with certain contravariant functors defined on the category of finite dimensional unitary representations of G with values in the category of finite projective bimodules over the fixed points of algebra. So that's basically, I have a strong feeling that this contravariant functor on the category of finite dimensional unitary representations of G into these bimodules, that this is somehow strongly related to your factor. And there is this called reconstruction. It's a natural way to, because basically what he says, aha, I have such two associated bimodules. I mean, they're not associated, they're just given sort of in this by this functor, and then I say how I multiply it, how I get the algebra. So there is a reconstruction theorem. Definitely, I'm not making any claims, but I would be shocked if these things were not related. So definitely, please have a look at this paper by Djurdjevic. It's on the archive. Basically, if you type into Google Tanaka-Klein and Djurdjevic, it will pop out immediately. Okay.
Is it published? Is it published?
I don't think so. I don't know, but it's not a reason to discredit this paper, since Mitchell has a very particular attitude, and this is why his papers are often rejected. But I can assure you that this is mathematically a very, very good and valid paper. Remember, Ludwig, we are also working with Djurdjevic, but it might be published. I just don't remember. But definitely, remember, Ludwig, we're working with Djurdjevic's braiding. This is a really good paper, where he extended Kornowicz's ideas from quantum groups to quantum principal bundles when it comes to braiding. And that's this is a beautiful paper which was never published. This one maybe was published, I don't know. Doesn't matter, it's on the archive. If you want to cite it, then you'll just look into it. very much.
I appreciate this, and I mean, I guess it's also related to this theorem where you have this unitary tensor functor, unitary
Yeah.
systems. I think one of the reasons, or one of the things why my theory is so nice is because you can actually do computations with these vector systems.
Yeah. No,
Sometimes it's hard to do this with the functors, of course. I mean, I just to promote that these vector systems are very useful for doing computations.
no, I absolutely love your framework. So that's this is how I like it. But somehow. Okay, I thought somebody was saying something, but I definitely believe that we should relate it to what was done earlier, because maybe we can learn something from what was done by Jurjevic, and this paper is definitely very good.
Piotr, Stefan?
Yes.
Just a sort of footnote to what Piotr said. I mean,
Yes.
there's a recent paper, and I don't think, I mean, Thomas Weber is in the audience, but
No, he's not.
maybe by three guys, including Thomas Weber, on the Jurjevic approach to quantum principal bundles. And this is this year.
All right.
Wow. So that's
So
really
maybe
recent.
this is worth looking at. as
Okay. Okay.
well. It's on the archives, yeah.
Okay. And do you have what the name of the paper, if I may ask?
On the Jurjevic approach to quantum principal bundles.
all right.
Just like
Wow. So that's
okay.
thank you, Andrew. Thank you so much. Yes. So and another one, you remember when I was asking Ludwig a question, if it's also a déjà vu for him. If you want to see the calculations I was referring to, then there is a 2004 comparative paper by Brzezinski and myself called The Chern-Galois Character. It's only 4 pages. And the calculations you're doing look to me the way we obtain out of a strong connection and the representation of a quantum. Okay, we are more general because we talk coalgebras, but okay, you can fix your coalgebra to be the half algebra of a Lie group, okay, compact Lie group, and then it all is part of a game. And we show how out of a strong connection construct an idempotent representing the associated projective module. So representation and a strong connection, and I give you a projection. So somehow the calculations you are doing remind me of what we were doing over there. And the general formula is very complicated and not so easy to grasp. I'm saying it because people complain about it. But if you take the case which is one-dimensional, then things become much easier. And then I'm just curious. I mean, they must be somehow related. So these are my my 2 remarks, and maybe now we will ask some questions. So any questions from anybody? No, Matthias, no? Anybody on Zoom?
Oh, I have a question.
Okay, go ahead. Just show yourself.
So
Thank you.
my experience thinking about differential calculi on total spaces induced from those on the base space and those on the structure group tells that there are different ways to lift the calculi to the total space algebra. And so I was somehow expecting some freedom, some choice also for the spectral triple construction. While as far as I understood, this is not the case, and I wanted to ask Stefan whether there is a specific reason for that. You can pinpoint.
I mean, that's a good question. I'm not completely sure what you mean by the freedom in the context of this differential calculus. But I mean, here, as I tried to point out, I mean, there's some freedom in the sense of the isometries that you choose. But
Yes.
so I was not able, or I didn't do it, to see like how much the whole construction depends on this isometries. I mean, it's just a very straightforward and convenient way to construct a spectral triple. Hard to say if, probably maybe other ways, or would be interesting to relate this differential calculus in this way. It's hard to say. Can you maybe give me an idea what you mean by there's some flexibility or some freedom?
Well, just as an idea, think about the easiest case of a smash product algebra.
Mm.
Then when you go to the differential calculus, you want, in the end, what you would expect is a smash product of exterior algebras.
Mm.
So you have to lift the action from the to the graded components, to the higher components, not just the zero component.
Mm.
And there is some freedom in this lift, usually, that you can choose consistently.
What we haven't done, and maybe this is something what you're referring to, is once you have the direct operator, you can look at the differential calculus generated by this direct operator. And here we haven't looked in how this is related to the base space and the group. So maybe this is something that could be done. But this is nothing we have thought about in this context. And of course, then once you have the lifted direct operator, you could ask, like, how is it related to the differential calculus on the base and the structure group? But I haven't done this. So maybe this is related to what you're saying.
Yes, I would say that's another way to, how to say, to check and to relate the two approaches.
Mm-hmm. Okay. You?
Okay, anybody else? Andrzej, Ludwig?
Yeah, I do have a question.
Yes.
Okay, so this relates somehow to the question by Paula. Basically in your construction, you lift and you get one Dirac operator, not a family.
No, we get one.
Is it correct, Stefan?
Yes, it is correct.
You get
yes.
one.
One.
So this is somehow, somehow different from what we were doing with Ludwig, where our focus was somehow on getting a family and relate this family to exactly, sort of incarnation of strong connections. So algebraic construction of strong connection. So my question would be, I think it should be generally possible also in your case. So this is one question. So do you think it's possible, to more generally link some sort of algebraic construct like connection to the lift and to the Dirac operator on the total space?
And by connection you mean now connection 1-4? Like this connection 1-4. So this kind of thing. That would be very interesting to investigate, I would say. I didn't see how, because I think I understand algebraic context, but again, what I tried to say before, I stumbled into many problems in the C-star algebraic setting with the strong connections, kind of things. But I would be happy to look into this and work this out, see how this is related. But if this is related, I think this is exactly what you're saying. It should work along similar lines.
Yeah. My second question is, generally, if you leave the Dirac operator, there's something that you can construct, like the length of the fiber. So this is the lift that you consider is the lift for the constant length of the fibers. Is it true?
Actually, there was a question that I also had, but I never got an answer to this. It was not. We didn't look at the length of the fiber. No, but this was a question that I had, but was
okay, good.
But it's good that you. Maybe I write you an email and then we can discuss this.
Sure. Absolutely.
Yeah, because when I read your papers, then there's this notion of the length of the fibers. I couldn't really translate it, or maybe I didn't understand it well enough. But maybe this is something worth to look into.
Yeah, and maybe I also mentioned, that our motivation was, and the classical motivation, I think it might be related. There's an old paper by Christian Bear and somebody, I don't remember the second author, that was doing exactly the thing, you know, classically, I think for the U1 or maybe for the general construction, yeah, just lifting and relating the Dirac operators, yeah.
I think Aman Bear, no, Aman and Bear, something.
Aman
like
and
that.
Bear, yes,
Yeah,
thank you,
something.
Ludwig.
Mm.
Bernd Aman and Christian Bear, yeah.
Yeah.
Now, another thing is they went from base to total space, but we tried also to go from total space to base with Andrzej in
Yeah.
our paper. So it's another direction one should consider. Okay.
Yeah, the question is then how the Dirac operator factorizes somehow.
Exactly. If
Yeah,
it's invariant
exactly.
properly. Yeah.
And this then also related to KK theory questions. Maybe. Yeah, and for this you need the fiber. I mean, this notion of the length of the fiber, I think, right? Because I mean, I don't think, I mean, our Dirac operator is not G equivariant, I think. And what if this is not G equivariant, it's hard to factorize it. So I mean, a couple of things to consider.
Okay, anybody else? Adam, Christian?
No, I don't have any question. Thank you.
Okay, so let me wind it up with the following questions. So if you look at your factor system at your omega, what would be the property of the factor system itself that would say, aha, so now this is cleft or stuff like this?
Okay. That's a good question. I mean, cleftness implies that. Okay, I told you before that I consider this representations mu and h. And in the cleft case, this will always be the left regular representations on L2 of G. So, so there's some relation. So in the classical, I mean, in the cleft case, this will be the left regular representation on L2 of G, because then H is simply L2 of G in the cleft case.
Yes.
Otherwise, could I say? I mean, otherwise it's hard to say, other than that the elements are unitaries and so on.
Yeah, but then it's tautological. Yeah, because you see, there is a certain subtlety here. One way, it's completely obvious that if you are cleft, that all these associated modules, these gammas of yours, they are always free.
Yes.
But I've been wondering for decades, is the opposite true? I mean, if you have that all associated modules are free, can you prove to me that your bundle is cleft?
I mean, just a stupid first idea. I mean, how is that if you just look at a finite cover of the torus? Right? I mean, this is.
Yeah, this is exactly what is cleft.
Yeah, of course, this is cleft. Yeah.
This is cleft, and that's not the counterexample. This is cleft and not the cross product.
No, you're absolutely right. I was too quick, but yeah, I thought, I mean, it's cleft, but it's not a trivial bundle.
Exactly.
Exactly.
This is why I made this point that when you have a no cocycle cross product, that's a trivial bundle. The moment you put cocycle, you quit triviality.
Yeah. Okay. So what you're saying is that all your modules are trivial, but the algebra might not be cleft.
Yeah, I would be so happy to see a proof. I've been wondering for decades. Not that I was working on it, but it's just.
Yeah, just to see how this. Yeah, okay.
That's and it's very much into your ballpark, because you classify bundles, so you should be able to answer such questions, right? I mean, it's this kind of thing, right? I want to see, fine, so now all assessed modules are free. Okay, so this must be cleft, because you somehow get your structure out of these gammas. But you basically define your multiplication by saying how you multiply isotypical compounds.
No, you're absolutely right. But well, I think about this. I feel that it's not far away.
Okay.
Oh.
And my second question is, do you have any nice classification result in a concrete example of you give me some nice groups, some nice fixed points of algebra, and then you have classification of everything?
Yes, I have.
Okay.
I can also tell you where. So in reference number 4. So this is when you have compact abelian groups, you have a very nice classification in terms of classical group cohomology. So there things are really computable and yeah, you can.
Okay, excellent. And so what would be so you have abelian groups, okay?
Mm-hmm.
And what are your sister algebras?
The unital sister algebras, or what do you mean?
I'd like to see some interesting classification. I don't know. I give you
Okay.
the
Let me put it this way. I mean, the way we classify, I just need a page somewhere. The way we classify is okay, so you have the C star algebra B, and so you have a group compact. I'm an idiot. I was writing with a real pen. So you have the group G, and you have your unital C star algebra B.
Exactly.
And the way you classify is you start with the following. You start with the homomorphism from the dual group into the group of Morita self-equivalences over B. So, and then the question, so this is invariant for these free C-spherical systems with compact abelian structure group. And so what you can show is that when you have this, does there exist? Okay, maybe the other way around. So these are the things you start with. And in general, if you have a free C-star dynamical system, right, you always get one phi of A into the Picard group. And how do you do this? Well, the character maps to the isotypic component corresponding to the character.
Of course.
So this is the map. So now the question would be, if you start with this guy, just abstractly, is there a free C-star dynamical system, AG alpha, that has this Picard homomorphism? And then, well, the first result is that there is an invariant in the 3 cohomology on the dual with values in the unitaries of the center of B. And if this class vanishes, then, so if this class vanishes, then there exists such a guy, a free C-star dynamical system with this Picard homomorphism. And then you can show that, so the extensions of B by G with Picard homomorphism phi, this is a, how do you call this? Okay, you have a simply transitive action by the 2-group cohomology of G with values H2 of G star U center of B cross. This is transitive. So it means if this if this characteristic class vanishes, you know that this is non-empty. And once you know it's not empty, basically H2 characterizes all extensions. So it acts transitively on the set of extensions with this Picard homomorphism.
And freely.
And freely, yes, and freely, yes, exactly. So yeah, I mean, basically it tells you that you have one, and then all others are classified by this H2 group cohomology.
Okay, but concretely, I want B to be the sister algebra of a Polish quantum sphere.
Of a what? Aha, yeah. I mean,
Want to see and G, let it be U1. So G star is integers. So
yeah, sure. But then the problem already starts with what is the Picard group of the Potter sphere?
Mhm.
I mean, I think this is also something. I mean, I think some people in the 90s, they have computed the Picard groups. I mean, of course, they're known for matrix algebras. They're known, of course, for classical C-star, also for commutative C-star algebras. That's a cross product with the automorphism group and the line bundles. And for the quantum torus, people have computed this Picard group. But I think it's an interesting problem, for example, to work in this principal bundle case, to compute the Picard group of C-star algebras.
Okay, so take B to be this quantum torus sister algebra, then what would be the classification picture?
Now I have to, I mean, again, I mean, given this is known here, this guy, right?
Mm-hmm.
And then as you say, okay, I take the torus, okay, then I have a set here, perfect, no problem.
Yeah.
I just choose, right, my isotopic component at the generator. Then I can, well, in this case, it's manageable to compute this characteristic class. And if this vanishes, well, you're happy.
But you don't know if it vanishes.
No, you don't know that it vanishes. If it vanishes, you know that there is one. I mean, this is an abstraction. The characteristic class related to Picard homomorphism is an abstraction for the existence of such a bundle that has the Picard homomorphism.
Yeah.
But again, I mean, you need to know something about the Picard group. Otherwise, you cannot do computations. And then when we wrote this paper, there are a couple of examples about Picard groups are known. But of course, I mean, like, it would be interesting. What is the Picard group of the? I mean, I didn't know. I mean, I didn't find anything about the Potter sphere. I mean, anything. I mean, there's not much known about Picard groups of C-star algebras.
And let me tell you why I think this case is interesting, because, of course, the case here of a quantum torus is very interesting, and we have this non-trivial projection. And we like it so much, right? It was the birthplace of non-commutative geometry. But there is also a certain no-go theorem by Francesco D'Andrea that this powers Riefel idempotent, which gives you this non-trivial generator in the case here of the irrational rotation sister algebra, the quantum torus sister algebra, that this cannot come as an associated bimodule from any Hopf-Galois, from any non-commutative principal bundle. And that's something very interesting, you know. If you can, how can you, if you look at K theory, element of K theory over the sister algebra, can you find a non-commutative principal bundle such that this would be associated with it? Classically, that's obvious because that's a frame bundle. To have a vector bundle associated with the frame bundle. And by construction, your vector bundle is associated with its frame bundle. So that's completely obvious, and we are totally missing this in non-commutative geometry. I mean, maybe not totally. We can try to somehow go around it, but this is yet another story. But it's, I think in this context, when you classify these bundles with a given fixed point subalgebra, this would be very interesting to see what it actually is explicitly, not in terms of ignoramus per ignorabimus, okay? But I'm just pointing you why I believe this case of a quantum torus is interesting from this classification point of view. So let me really finish by asking you, so do you have any non-commutative example where you would really have like a complete picture? Give me a non-commutative sister algebra and some nice abelian group, and then tell me, okay, there are only two classes of bundles, and that's it.
I mean, technically is wait. Yeah. Okay, maybe another thing. Maybe the other way around. If you look at the quantum Hopf vibration, right?
Okay.
So there you have an action of the circle of the one torus. There's the Pottl sphere, there's the fixed point algebra.
Yeah.
Then you might ask, all right, I mean, I have a fixed point algebra, I have an action.
Yes.
Are there any other
Yes.
species that are in this class? And here the answer is no. Because, well, you can show that, well, so H2 of theta always vanishes. So there's only one, like the Pottl sphere is the only extension in this class with this pK homomorphism. Simply, I mean, because H2 of theta vanishes. Or in more general, Hn of theta m vanishes if m is smaller than n. So we have this kind of results. But again, yeah.
But you have length spaces. I mean, I can give you countably infinitely many non-isomorphic, non-equivalent, non-commutative principal bundles which are U1 bundles and which have Pottlish as a fixed point. So you can take all length spaces, right?
Yeah. But again, I mean, if you take one, right? If you know they exist, then you know how many exist in this class corresponding to the pK homomorphism. Right? Because, I mean, this is given by this H2. And this you can compute.
Sure. But what interests me is I have a group and I have an uncommutative sister other. And I want to see all possible non-commutative principal bundles up to, of course, equivalence with this structure group and that fixed points about. And that's what would be for me very interesting.
Yeah, but again, if you have one already,
you can always have a trivial one.
Yeah, I mean, the trivial one does, I mean, I know it's not true. You cannot always have the trivial one. I mean, if you start with one, it's not so clear. I mean, it depends on the pK homomorphism.
No, I mean, trivial bundle always exists. Come on.
Yeah. No, sure. Yeah, it exists. But I mean, I'm just saying if you start with any free-C dynamical system, then the trivial one is not necessarily in the class that corresponds to
this. Of course, but that's not the question I'm asking. This is not what I'm interested in.
But here again, I mean, if you start with the free one, and then you can, I mean, you take a co-cycle in H2, and then you can twist the multiplication with the co-cycle, and this gives you, I mean, this gives you new C-star algebra. I mean, what I'm saying is you can use this co-cycles very explicitly to twist the multiplication that you have with the one you started with to get a new C-star dynamical system. What I'm saying, if you're interested in one, then you have the class that corresponds to the pK homomorphism, and then you can twist the multiplication by this co-cycles, and you get other free C-star dynamical systems in the same class. That works very well.
Yeah. But I'm not interested in different C-star dynamical systems in the same class. I'm interested in different classes of C-star dynamical systems.
Yeah, but again, I mean, you need some kind of invariant, and the one that we use is the pK homomorphism, and then you can very specifically say the extension that have the same pK homomorphism. I mean, maybe we have a misunderstanding what we mean by this in the same class. I mean, class in the sense of all free C dynamical systems which are having the same pK homomorphism. Yeah.
Okay.
Maybe just last remark. I don't know. Maybe this is also a little bit interesting to you. Is we have a result using this factor system saying that if you have finite coverings of the quantum torus, must be cleft. Or maybe I mean this uses also this projection of the factor systems and so on. I mean,
that's very interesting. I like it. Yes. Yeah, this is a very nice result. Yes. Yeah, I like it. Yes. Thank you. Okay, thanks Stefan again. Thank you so much.
Thank you.
Let me stop recording.